This is problem number 2 from chapter 17. In this problem, the solid cylinder has an outer radius capital R and a height h and is made from a material having a density that varies from its center as k plus ar squared, where k and a are constants. Determine the mass of the cylinder and its moment of inertia about the z-axis. So in this problem, we have a non-uniform mass density. So this is something that we never saw in Physics 261. In Physics 261, it was volume charge density, but it was always a uniform density. Here it is not a uniform density. So as R increases, the density is increasing. Okay, so first let's write out our equation. So for the moment of inertia, we have the integral of R squared times rho integrated with respect to V. This is equation 17.2. For this problem, we are going to use a shell element, and this is what they talk about on page 411. Now, we are going to see different problems in which we could solve it using the shell element or the disk element, or not using either one of them. So you don't necessarily have to solve it this way, but this problem is going to be easier to solve using a shell element. Okay, so you'll see how that works in this problem, and then later on we'll talk about how you decide which element you want to use. Okay, so rather than choosing a little piece of mass like this and adding up all the little pieces of mass by doing an integral with respect to m, we're integrating with respect to v, but rather than picking a little mass like this, we're going to look at a shell. Okay, so we're going to make up all of the volume by adding together shells like this. So I have a cylinder here. There's my cylinder. And I can pick a shell which has a very small width. Here they call it dy. I'm going to call it dr instead. So here's my shell with a very small width, dr. The height of the shell is the same as the height of the cylinder. And I can take a bunch of shells like this with very small widths and add them all up together to give me the entire volume of the cylinder. So rather than making up the entire cylinder by adding up small little pieces of mass like this, I'm going to make up the whole volume by adding up these shells that have a width of dr. Okay, now they tell you on page 411 that dv for the shell, so that's the volume of my shell, which has a small width dr, is equal to 2 pi y, but I'm not using y here. I'm going to say this distance here is r and the width is dr. So I want the volume of the shell, and so 2 pi r, that would be the circumference that I have here. The circumference times the height here, which is h, gives me the area. If I were to cut the cylinder down the side like this and unroll it, that would be the area that I have. Then I have to multiply it by the thickness here, which is dr. So that is the volume of this shell. Since we've been talking about Physics 261, this 2 pi r times h, remember that's how we find the area of the outside curved portion of the cylinder. So if you take your cylinder and you cut it like this and you unroll it, this distance is h, that's the height of the cylinder. And when you unroll it, this distance from here to here, that's the circumference, 2 pi r. So this has an area of 2 pi r times h. Then since we're looking for the volume, we have to multiply that by dr. Okay, so for the shell element, this is what I use for dv. So now I have r squared times rho, but rho is not uniform here, so I have to put this in for rho. So I have k plus ar squared times dv. dv is 2 pi r times h times dr. Okay, so now I just have to integrate with respect to r, and I can pull out the h and the 2 pi. I actually kind of skipped this here. R squared came from this equation. I want to make sure that that's really supposed to be r squared. So that's supposed to be the perpendicular distance from the axis of rotation to your small piece of mass. This is r here. That is the perpendicular distance from our axis of rotation here. So r is really the r that I defined here. So that's good. And I have another r here, so that becomes r cubed. So this is r cubed times k plus ar squared dr. And then I can distribute the r cubed, and I have k times r cubed plus a times r to the 5th integrated with respect to r. To make up the entire volume, I'm going to start here when r is equal to 0. I have to add up the volume everywhere where there is mass, so that gets me all the way to the outside, which is when little r is equal to capital R. So I go from 0 to capital R, adding up all these shells everywhere where there is mass, so all the way to the outside of the cylinder. Now I can integrate. So I have the 2 pi h out in front. When I integrate kr cubed with respect to r, I get kr to the 4th divided by 4, plus when I integrate r to the 5th with respect to r, I get 1/6 r to the 6th, and then I have my constant a. Then I put in my limits of integration. When I put in the lower limit of integration, I get 0. So this just becomes 2 pi h kr to the 4th over 4 plus a r to the 6th over 6. This is the moment of inertia about the z-axis, which is what they asked me to find, but they also asked me to find the mass. Okay, now we're going to find the mass using what they give me here. So if dm is equal to the density times dv, is equal to the density times dv, I know the density, so I can just integrate on both sides. When I integrate dm, so I add up all the little pieces of mass and I get the total mass. Okay, so the mass that I'm looking for, let's call that little m, is equal to the integral of the mass density, which is k plus ar squared, integrated with respect to dv. Now, the reason that we have to do this, if we go back to what we had last time we had a uniform density, which meant we could just, when we found the, well, we could just write the expression here, which would give us the mass by doing the densities equal to the mass over the volume. But we can't do that here because this actually came from what we had here. And if it's a uniform density, then this is true. But if it's not a uniform density, you actually have to do the integral here. Okay, and to do the integral, we're going to use the shell element method, and so we're going to replace dv in this integral by what we have up here. So we're going to use this again. Now, you don't have to do it this way, but it just makes the problem easier to use the shell element. So we have k plus ar squared times dv, which is 2 pi r times h times dr. The difference between what we have here and what we did to find the moment of inertia is that for the moment of inertia we had an r squared here, and for the mass we do not. Okay, so other than that, everything's pretty much the same. We can pull out a 2 pi h. distribute this r, so now I have the integral of kr plus ar cubed, integrated with respect to r, adding up everywhere we have mass, so going from 0 to the outer radius, and that gives me 2 pi h. For my integral here, I get kr squared over 2. When I integrate r cubed, I get r to the 4th over 4, going from 0 to r. And I have 2 pi h kr, that was squared, over 2 plus ar to the 4th over 4. That gives me my mass. Okay, so now I have my mass and my moment of inertia, and that concludes problem 2.